I'm John Avenson, and I live in an NREL designed passive house from 1981. Today we have Bill Lucas. He's a passive house certified builder, a passive house consultant, Building Performance Institute certified professional, a master mechanical and licensed general contractor. He got into straw bale houses in the 1990s. He's managed and built several homes, the net zero, two of those of which were featured in the Boulder Green Building Journal and the Conservation Magazine. So he's seen a big potential in the market for retrofitting energy wasteful homes. Bill holds a bachelor's in Japanese, a Bachelor of Science in Environmental and Biology at the University of Colorado, and was CSU's first green building certified LEED program. So he lives in Golden with his family, and take it away, Bill.
Awesome. John, thank you very much. So some of the questions that we're going to try to answer today, and feel free to interrupt. This is very informal, but I try to answer any questions I can. But what is an air source heat pump? Most of you probably know. Some of you know probably more than I do. But where can they be installed? When does it make sense to install? When doesn't it? How much do they cost? That's an important fact. I mostly work on residential, but we'll talk a little bit about commercial and commercial applications for heat pumps, and not just air source heat pumps. Heat pump technology is similar, whether it's air source, water source, ground source, geothermal. Geothermal and ground source should be separated, but we talk about them the same. Who should install it, and some installation tips if we get there. So before we talk about those things, I just want to show you a brief background about where I came from. So I did go to the University of Colorado. I grew up in Morrison area, not very far from here. Went to Bear Creek High School, lived in Japan for a year. I did a Rotary exchange program in high school. Came back, majored in environmental biology and Japanese at CU. And I really love working with my hands. I always have. I love wrenching on bikes. I love pottery. I love building things. And I thought, how can I make money and also work with my hands? So I started building homes. But I'm also a deep greenie. I really want to reduce my carbon footprint. I see the writing on the wall. This was 20 years ago, 30 years ago, and we've seen it coming. It's now pretty obvious what's going on. But this has always been part of my life, is trying to reduce my own carbon footprint. And so I started building what I thought were the greenest homes we could. And I would still argue that are some of the greenest homes we can build from a number of different perspectives. So I started building straw bale homes, experimenting with different plasters. This is actually from Pioneer, which is right up here on 93, which makes a great adobe. So mixing different, playing with different clays and different paints, all local, all natural as possible. So I built a number of straw bale homes. This is the first straw bale near net zero in Fort Collins that was permitted. There were some straw bales that were unpermitted before this time. But this is a non-load bearing, so there's actually timber in here. But this is lime plaster on the exterior, adobe plaster on the interior, all recycled tiles. All these tiles came from Yellowstone. They took down one of the old lodges, and all these beautiful clay tiles from 1911 and stacked them on pallets, and we took a bunch. So this is what I did for a number of years. This was a Martin Acres single-story ranch house that we retrofit into a net positive energy house. We use SIPs here. We did a lot of spray foam, which I'm now moving away from a little bit now that I'm more into passive house, and the global warming potential of some of these spray foams is a little bit onerous, and so we need to be careful about how we use them and when we use them and if we use them. So these are just some of the projects that I worked on. This is a net zero energy house in Boulder up by the old hospital. You can see the earth clay being on the bales here. You can see the little truth wall, all lime and adobe plasters on the inside. Use a lot of local beetle kill lumber, etc. All the floors, etc., etc. So this is what I do now. So about 10, 12 years ago, I lived in an old home in Denver, 1920s bungalow. Everyone around me in Highlands had the same type of house. They were all very uncomfortable, not very energy efficient. So I started a company, not only to retrofit my own house, but to retrofit the houses around me. And so I had a number of crews running. We always started with an audit. You really need to know what you're getting into so you can prioritize. We can all say, hey, I want an air source heat pump for my house. But maybe you've got a big gaping hole somewhere, and that should be taken care of first. So I really want to encourage people to think about audits and gathering information if they're thinking about tackling their home, it's a journey. This is not you get to do everything all at once. You really want to prioritize your journey, and safety things always come first. There's always carbon monoxide issues. Not always, but sadly, often there are carbon monoxide issues, mold issues, air quality issues, insulation problems, air leakage problems. Those are fundamental things. And I often recommend that we take care of those things before we invest in this more expensive technology, because we want to size things appropriately too. You can put as much solar on a pig and you can make it a net zero house, but that's not really the approach, right? We want to make them efficient as well. So I do this now. This is what my company does. We retrofit, and I say we, it's now just me. I used to have a number of employees, not anymore. It's just much easier to be with my children and to spend time doing the stuff I do. So this is a mini split that I installed just probably a month ago at a gal's house down in Denver. I do a lot of airflow testing, still do the insulation, air sealing work, retrofitting insulation. There are other cooling sources that are also very, very efficient. I'm a big fan of evaporative cooling in this climate in particular, whole house fans, natural ventilation. We have traditional furnaces, et cetera, et cetera. But I'm a building scientist, that's what I do, but I do mechanical work as well. Okay. And this is some of the stuff. So traditional air conditioner, whole house fan, tankless water heaters. We're starting to move, and I'm starting to push my clients more towards electric rather than gas. You can't control your carbon footprint so well with the gas, but you can with the electric if you hook up to renewables. And even Excel now, and we've had WindSource with Excel for a long time, but now we have the ability to say, hey, they have, I think it's called Energy Connect or Renewable Connect now. What is it?
Renewable Connect.
Renewable Connect. So you can now buy credits. You can buy solar power from Excel. And they raise, so instead of paying 14 cents a kilowatt hour, you pay 15 or 16 cents a kilowatt hour. But you can say, I demand 100% of my electricity is technically coming from solar. Well, that's cool. And if you do that, and everyone does that, I talked to a client yesterday, and he had no idea. And I really encouraged him, let's do that. And then these technologies for heating start to make more sense. In the 1970s, everyone thinks about electric resistance heating as being incredibly inefficient. Well, electric resistance heating isn't inefficient. It was the houses that were inefficient. You know, some of the most efficient houses, that house in Boulder, that last one I built, I put electric resistance heating in. Why? Because I don't need it. That's a passive solar house. That'll come on maybe a week, the entire year. Okay, so I put in a $200 heating thing instead of a $6,000 heating system. I saved a lot of money. And what's the difference in carbon? Not much. I mean, this probably is a lot of embodied energy in this versus a little baseboard. So there's an appropriate time for different technologies. Okay, some other things. So Windows, Todd Collins from A&E Building Solutions. This is, he's the Alpen rep. Alpen is a very high performance window out of Boulder. They're very nice windows, and so install some of those. This is also a product that Todd reps, but my client didn't buy this from you. But this is a passive house up in Boulder. He's wrapping his house in rock wool, and then of course renewables and solar is. We used to think about it as the cherry on top of the efficiency sundae. I don't think about it that way anymore. It's just part of what you do when you are building a home or even retrofitting a home. I'm going to install a new furnace. Well, you should think about solar too at the same time. Financially, in some cases, it makes more sense to do solar before any of this. The payback is really that good. Okay, so why do all this? Just a little context. We all know this probably. Just quickly, 130 million existing homes in the US. 1% of those, 1.3 million new ones added each year. The average uses an obscene amount of power and of electricity and of gas. It's ridiculous. We can make homes, and we are making homes now that are so much more efficient. And it's not like we're taking away from the old homes. It's not like you have to eat your vegetables, son. You know, it's not a burden for the homes to be more energy efficient. They're more comfortable. They're healthier. They're safer. They cost much less in the life of the home to build these homes. So we're not giving anything up by making these homes more energy efficient. And it's 21% of all U.S. energy use is from residences. And the other balance is made up from of the 50% of all the energy we use in this country is from buildings, commercial buildings, etc. It's a huge, huge amount. And the good news behind all of this, every one of these can be net zero energy. This really isn't that hard, right? I mean, DOE's got their great program right now with zero energy ready homes. California, less than a year and a half. All new homes, net zero, required. California, that's the 5th largest economy in the United States. All homes are required to be net zero, not net zero energy ready, net zero. That's a big deal. If we can do that there, we can do it here, and I encourage us to do it here. Paul?
No, just a quick caveat. It's the 5th largest economy in the United States.
Sorry, in the world. In the world.
Yeah.
In the world. And lots of different climate zones. We're not talking about everything on the Santa Monica, the pier where they have a constant of 65 degrees. This is in the Sierra Nevadas. They're going net zero for every new house in the state. And we should be following that. And I think we will at some point, but hopefully sooner than later. Europe is definitely moving in that direction much quicker than we are here. So I know you're all helping to promote this. Okay, so what's a heat pump? In most basic terms, a device that transfers heat from a colder area to a hotter area by using mechanical energy. Okay, heat pumps that you may not know that are heat pumps. Refrigerators, heat pump. Air conditioners, heat pumps. We have heat pump water heaters. We now have fancy heat pump water heaters where the tank and the actual condensing unit are separate, just like with a mini split air source heat pump. Basically, and we could go into this very deeply, this is the refrigerant cycle, but basically, oh, I brought a prop, but I think it got left in the other room. So I brought my bicycle. I have a little CO2 cartridge that I plug in, and I can pump my bike tire up really quick. When you have a drop in pressure, that CO2 cartridge gets really cold. That's basically what happens with a heat pump. There is a liquid or a gas, there is a material, a refrigerant, that transfers between the outside unit and the inside unit through copper lines, insulated copper lines. They're under very high pressure, 500, 600 psi. And depending on if these are in liquid state or gas state, there's a certain temperature that they are. And so this machine controls the temperature and when it expands to absorb heat. And basically, this cycle can reverse. You can say, I want the expansion to happen inside in the summer of the gas, of the liquid to a gas, so it absorbs heat from the air. Then it goes back to the compressor, gets put back into a liquid again, and it just goes over and over. The compressor drives the cycle. And in the winter, it goes the other way. The problem, and you actually mentioned this earlier, because you were talking about heat pumps 20 years ago. 20 years ago, or 30 years ago, or 40 years ago, heat pumps didn't have the ability, because of the compressor technology and other things, to get enough sufficient heat out of cold air. But we all know that even 0-degree air is still a lot warmer than absolute zero. There's still heat in that air. And we now have technology that continues to improve and improve and improve, where we now have the ability, even at this unit goes to -17, and it will still put out at -5. We'll look at a sheet on this machine later. It still puts out 100% of its energy at almost 200% efficiency, and I'll explain that in a little while. But on average, this machine might have 400 or 500% efficiency. But this is now a cold climate solution. These weren't 10 years ago, but they are now. And we're installing these in Alaska. I was up in Evergreen just the other day. Evergreen's a lot colder than it is here on average. We now have the ability to use heat pumps to create heat efficiently using electricity, or more efficiently using electricity. Okay? So that's basic. And whether it comes from the ground, whether the fluid that goes through these pipes, whether it's in the ground, whether it's in a giant lake, or whether it's actually in using the air, there's always heat there. So we're moving heat from one place to another, the ground, the air. The ground's nice because it's a constant 50 degrees here. But you got to dig, and that's expensive. And there's nothing wrong with digging. And I know Martin here in the middle just got back from Germany, and I have some slides later from Germany. I was just doing some passive house stuff in Darmstadt, Germany earlier this year. And they're doing geothermal loops for entire multifamily areas. So before they put the apartments up, it's all shared common heating. And in fact, what's the gentleman? Geos. And what's the guy's name? Norbert? Norbert is done the same thing right here in Arvada. So
he has it. Just
not.
That was the original plan.
Oh, so they switched. Now they're using minis? I think they are.
Geothermal unique.
Okay.
Teach unit.
Okay, so it was a shared geo, but it's not anymore.
And it varies by unit.
Okay.
So he's got a different strategy for different units.
Okay, okay. Well, that was the dream at one time.
It was the dream.
But in Germany, they're doing it, and it's really cool stuff. So but this technology is not that much less efficient than ground source, and it's a heck of a lot less expensive because you don't have to install all this stuff. There's not the infrastructure there. Okay? Okay, so air source heating and cooling pumps. Remember, mechanical energy, we're moving heat. So we can have small, little outside units that might go to an indoor head, like this one right here. We can have this connected to a whole duct system that distributes out throughout a house. We can have larger heat pumps that can replace your air conditioner and furnace. So these are heat pumps now because we have the technology. This is a Carrier Green Speed that works down to, this one works down to about -5 and still gives you heat. So you can basically put this in place of your new air conditioner when you're replacing your old 10 SEER with this, and it will produce the heat as well. You're fuel switching though. You're not using your furnace anymore. You're not using gas. You're using electricity now. But it does not costing you anymore because there's an efficiency here. So gas might be 1/3 the cost per unit of power as electricity is, but this electricity you're leveraging because you're moving heat from an existing source, right? So on average, you're just fuel switching. So if you're getting solar, if you're going to Excel and saying, hey, I want to sign up for wind source or whatever renewable energy options they have, you are really lowering your carbon footprint. And your cost doesn't change. You're just swapping sources. Okay? These are appropriate for certainly small and large. And I'll show you some later. This is actually, I was out on Union, in like Sims and Union. And this is a big apartment complex. And I look out, and each one of these is an individual like 3 or 4 ton AC unit. And I'm like, what a waste. What a huge waste to have each one of these units individually heated and cooled. You know, like we could, it doesn't make sense. But anyway, we do a lot of things that don't make sense. Air source heat pump terms. I'm not going to get too much into these. You can ask me about these more later if you're curious. But one of the most interesting things that I think here is this coefficient of performance. And I think it's going to actually make sense if we look at one, but there are all sorts of things that we can measure these by. And rather than looking at this one first, let's actually go online really quick. So I just took some screenshots. I am a Mitsubishi Diamond dealer. I install Mitsubishi. I like their stuff. There's lots of good heat pumps out there. Fujitsu makes good heat pumps. LG makes good heat pumps. Daikin makes good heat pumps. Mitsubishi, I like them. I think they have great technology, but they're not the only one. You don't have to get a Mitsubishi in order to get a quality heat pump with great performance. You can go with lots of others. They just have a very, very good service record. But this is all open source. You can go online and you can go to, it's called MyLink Drive, and you can go and see all these different things that they have. So I'm going to show you some of what they have to kind of broaden your understanding about the heat pump world. So what I did from here is I click on the M Series, which this unit is, and it shows me, okay, here's all my outdoor equipment I can pick, and you can pick all these things. But again, I can have a floor-mounted indoor unit. I can actually have an air handler indoor unit connected to that. So I can connect to ducts. This is horizontal ducts. This is traditional ducts. I can have a ceiling cassette, or I can have this, what most people think about with these heat pumps that they see in Europe and Central America and Asia, which is the wall mount. Then I go to, okay, this is this unit, and it has all of this information here. And then it has the specifications. So just to break down some of these things. So you'll notice, so heating at 47. it has a certain capacity in BTUs, okay? So this is how many BTUs this thing can put out at 47. When we dropped to 17, the output dropped. It's not surprising. There's less heat in 17-degree air than there is in 47-degree air, right? But this is a 06. This is a 6,000 BTU unit. They're giving me my capacity of greater than 6,000 all the way down to minus 13. So when you buy a rated unit and an engineer sizes this unit for you, you need a certain amount of heat to match your heat loss at a certain temperature. So I put the room and I model it in a computer, and I say, given those windows and the air leakage and the insulation levels, I need 20,000 BTUs of heat. Well, I better get a unit that's rated at 20,000 for the design temperature for that area. So then we start looking down here at the efficiencies. 33 SEER, I don't know if anyone knows about SEER values. That's really high. That's great. That's great. Like the highest we can get with central systems is usually 20, 22-ish. This is phenomenal. And this is kind of a fun one. So the COP, that means coefficient of performance. And I think the best way to describe coefficient of performance is if you have a watt of power and you put your toast down in the morning. Let's say it's just a watt. It's equal to about 3.412 BTUs, right? So for every watt, if you put it through a resistive element, you get, let's just say 3 watts. Well, with heat pumps at a certain temperature, this is like getting 4.6 times 3 BTUs, so we'll call it 15 BTUs, for every watt of power. So you can think of this as efficiency. This is 468% efficient. So we're leveraging that electricity to make more heat than we would by just using the electricity. That's cool. That's really cool, right? So, and even at lower temperatures. So down at 17, and it is getting warmer and warmer, I'm still at over 300% efficiency. So yes, a baseboard makes sense, but I'm using a third less energy than a baseboard at 17 degrees, and at 5, I'm still 245% efficient. Pretty cool, right? So these are cool things. Also, so this is a tiny one, 6,000. This is for a 500,000 square foot passive home. This is not an average home, okay? And I'm going to show you an example of that in a minute. But I also want to show you in the range, here is a 192,000 BTU unit. So this is the PURY unit, right? Now, their EARs and COPs, still not bad. They don't have the same data. They don't report it in the same way. But just like a furnace will have a capacity. A furnace in your house might be 60,000 BTUs, might be 120,000 BTUs, but you size it for your house. We can size these for your homes. And if we have a big building, we put multiple ones on, just like they do, or you can get very large ones that are 500,000 BTUs, 1,000,000 BTUs, right? So we have the ability to do this, but much larger capacities, okay? And another thing that's cool about this website and this MyLink drive, and you can go play on this site if you're interested, but this, where it says software, they actually have what's called DSB, Diamond System Builder. You can pick your system, and then it gives you all your options, and you can click and drag and drop, and it tells you what size line set you have, what the capacity is, how much pipe you have, and it's all open source. It's all free, so it's kind of cool. So you can just go on there and you can play and you can test what I have recommended for your house and see if I actually did it right. But it's just a spreadsheet. It's just an Excel project. So kind of cool. Okay, so how much do they cost? This is very rough. In Colorado, we have to have cold climate specific heat pumps. In California, they're not spending money on this fancier technology, which is called hyperheat. It's kind of like a heat pump on steroids. This is their most efficient cold climate model. We need that in Colorado. It gets cold here. Our design temperatures are 5, 0, -5. So for this unit to install, and again, it depends on electric, I need 240 volt. Well, how far, line set complexity, am I running from this side of the house across a basement and then going up and then trying to get to a second floor loft, and is it 150 feet? That adds complexity. And so it just depends. But on average, these are, again, rough. $6,000 to $9,000, which is what you're going to spend on a furnace, right? And every single head you add adds anywhere from maybe $1,000 to $2,500. So the nice thing about these units, too, is they are zonable. This has, I'm going to show you. So this unit here, this has a little infrared eye here, and it actually scans the room. Some people freak out about it and they want to turn it off, which you can because it looks like Terminator's coming after you, but there's no red light or anything like scanning the room. But it separates the room into like 1,000 different points. And it says, it's hot here. There's solar gain coming in here. And there's people sitting here. It's hot there. And so it will say, I want cooling here and I want cooling there. And then these vanes that are in here and here will direct cooling to those places. So it's kind of cool, and it does the same with heat. So they're much smarter than they used to be. They're very quiet as well, which surprises people. So there's actually a fan and a coil in here, just like there's a fan and a coil in here. Remember, these can reverse. So the maintenance on these, very little. You have filters that get washed. And these last forever. And you'll notice behind that filter, actually I can pop this off, I'm not gonna, but you can come up and look at it later. There's a radiator, right? You have refrigerant running between these two. This is where it expands or gets compressed, and that's where the heat is exchanged, okay? So pretty cool, very quiet. And wherever this is, you match it to your heat loss. I can get these in 30,000 BTUs for a single head. We could probably do this entire space with one unit. And in passive homes and homes that get really efficient, where we have minimal loss because we have, R5 plus windows, we have R30 plus wall assemblies, we're very airtight, you don't have that heat loss. And so you can have one unit that's on one side of the house, and these houses are so tight they all have some sort of ventilation system. That's sufficient to carry the heat and cooling throughout the house. So you don't need a zone in this bedroom, in this bedroom, in this bedroom, in this kitchen, in this living room, in this basement. You can have one, and it can condition the entire house. So that's kind of cool. Most homes that you and I live in, I lost my... Thank you for watching out for me. Most homes that I live in, that I audit every day, they're not going to be comfortable with one system in the living room, in the bedroom. And I get that question a lot. Is it going to cool this bedroom? Maybe. It's hard to tell, right? It's hard to tell sometimes. We have duct systems, and every room should have its supply. This is basically a duct. It's your supply. And depending on the house, it may or may not work. But modern homes, this is absolutely a good choice. Okay, where can they be installed? We already talked about this. They can be ducted. You can have central room. Again, you can connect. This looks just like a furnace, right? There's just a fan in here. Outside, they can be under decks. This is actually at Steve's house. So Steve bought this very efficient Fujitsu. You can have ones that look like baseboards. And this is in new construction, and you'll note that I put drywall behind this because I need to run my line set, which needs to be insulated, and my power and my condensate. And let's actually look at that in a second. So you can do these in new construction. They're relatively easy. Okay. There are brochures up here too later if you want to grab one, just for education. So these are also incredibly quiet. Because this is a heat pump and it's going to be working in the winter as well, you don't set them on the ground because it snows. And if snow builds up, it's not going to work anymore. So you have to set it on a stand. So these usually go on 18 or 24-inch stands outside because they need to be above the snow level. And there are things you can do in extreme snow areas to block them from snow, but it gets rained on, it gets snow on, it's all fine. You've got 4 things that are coming from that are connecting these units. So we've got our refrigerant lines, and I'm happy to pass these around. So being copper, you can bend it, but you can't bend it too much because it'll kink. And you really want this to be an integral one piece of copper from the outside unit to the inside unit. Yes, you can braze, but these are so fine. There's something called a linear expansion valve that's got 1,000 different settings. If you get any carbon from your brazing with a torch in these systems, it can clog that. So I don't want to braze at all. I like to do a compression, a mechanical fitting with these. And that's what Mitsubishi requires. They say, we're not warrantying this if you don't do that. There are new systems coming out with, like, you've seen the PEX that we use in like the shark bite stuff where you plug and play and it goes under pressure. There are things coming out that work like that, but this is the copper and this is the insulation. So you can bend it a little bit, and this is throwaway. So if you kink it, Craig, you're okay. And then you have a power line. So your main power goes to the outside unit, and then you've got four conduits in here, conductors in here. And they communicate, so it's your power, it's your communication, it's everything. So the only thing that runs to the inside unit is 2 of those and 1 of these. Now, what happens when you cool air? On a glass, if you have a glass of lemonade, you guys know that you get condensation on that. You get condensation on this coil, on the inside. Air conditioners dehumidify. When Carrier created the first air conditioner back in the 1800s, he wasn't creating an air conditioner. He was creating a dehumidifier. That's what he was trying to do. And that's what air conditioners do. They dehumidify. And that's one of the ways we feel cool, is because if we're in a room at 70 degrees at 70% humidity, it feels a lot different than a 70-degree room at 20% humidity. That 20% is going to feel a lot cooler to us. So these dehumidify. What happens to that water? It's got to go somewhere. So we have a condensate drain line. Now, I like putting units on exterior walls because then I can run this line to the outside. In some jurisdictions, some don't like that. But if I'm on the inside, then I have to run it to the outside somehow, and that's complicated. And if I've got a unit like this, where does this drain? Well, it doesn't. It gets pumped. I don't like pumps. I don't want anything extra that could potentially fail. Now, if I have to have a pump, I have a pump. They're made for it. They work. They shut off if they overflow so you don't get water damage. But I like to have units on exterior walls. Also, while these units, every one of the different ways of delivery has kind of different pros and cons. This is the quietest, is a ceiling unit. This unit, this type of wall unit, is the most efficient. Again, being an energy guy, I like to install these, and they're still exceedingly quiet. I mean, they're whisper quiet. You're nodding your head. You know, you live with them, and that's how you heat and cool your house. So I like exterior walls, but you've got condensate to deal with. In the winter, you also have condensate to deal with here, but that's outside, so who cares, right? A little bit of water drips off. Okay. Great question.
What's the question?
If it's below freezing and this water is dropping underneath this thing, it's going to freeze, right? Absolutely, you are correct. So they reverse the cycle. It's just like with an energy recovery ventilator. So you're bringing in cold air and you're trying to exchange air all the time, but this core, with this heat exchange core, can freeze up. And so they'll either shut off the outgoing or the incoming air and recirculate it so it's hot, or sometimes they even have electric elements. Those are both strategies that mini splits use as well. Yeah, it's an electric element, or they stop the cycle for a minute and they pump heat from the house back to the coil, melt it, and then start the process again. Okay, good question. Okay. So, in summary on where they can be put in, new homes, yes. Retrofits, yes. Sometimes a little bit more difficult. Commercial, look at these. These are all like 500,000 BTU units on top of a skyscraper. These are huge. And the big ones, called City Multis for Mitsubishi, have the ability to heat and cool at the same time. So they use some cool technology where you can have someone who's cold in apartment 10A that can be heating, and in apartment 11A can be cooling, which is pretty neat. Okay?
Just a quick question.
Yes, sir.
So the little one in front is for the executive office?
That's right. That's right. And then these, yeah, they needed a little extra capacity somehow. So they added this one. Okay, so I'm going to change topics here for just a minute. It's about 12:40, so doing well, and we'll be done in probably 10 minutes to ask questions. Okay, so what about load? I'm not going to go into this too much. We all know there's math that we can use to measure how much heat gain or loss happens in a room. And it's just a way to understand what's happening. But I'm going to use a real-world example. So these are some things that I use every day. In fact, I used this one this morning to run a quick calc to make sure I was right, which is super easy. You just say, how much heat loss do I have in this room? Add up your R values, add up your areas, figure it out. How much airflow is being accounted for in heat loss? It's easy. What am I losing in cubic feet per minute? Blah, blah, blah. You don't need to know these, but let's look at an example. So this is a typical heat loss or gain example. 400 square foot room, 10-foot ceilings, average. 13 walls, 25 ceiling. Maybe it's on slab, so it's an R1 floor. We have 20 square feet of R2 glass with a solar heat gain coefficient of 5. Air change per hour is 3. So that's about, 1.5 natural air changes. Again, you don't need to know all this. Say we're heating to 100 degrees, so that we have a delta T of, so it's 100 degrees outside, so our delta T is 30 for cooling, and it's 10 degrees in the winter, so we're heating our delta T to get to 70 degrees is 60. So that room on a cold day is going to take 21,000 BTUs per hour to heat it, and 7,000 BTUs for cooling. And this is very true in Colorado. Heating loads are always bigger than cooling loads, right? So anytime I install one of these, I size this for heating. If I size this for cooling, come winter, they're going to be sad. They're going to be cold, and I'm going to be sad because they're going to call me and I'm going to have to replace it because I made a mistake. You always have enough cooling capacity if you size it for heating, because the heating and cooling is very similar in capacities on these. Okay, so now let's look at where we should be building and where Department of Energy, zero energy ready homes are, where passive standards are. And this isn't even going super hardcore, but same room, same size, but we're going to increase our R value. We're not going crazy. We're not German here. So, sorry, Martin. So R25 walls, R50 ceiling, R25 floors. So we've gone to an R5 window. Again, not crazy. That's Alpen's lowest grade window is an R5. They're 5 series. They go up to 11, 12 now in some glass.
In the glass itself, they're up to
Glass is more
16.
than that. So, but overall value.
16.
So these are average. These are average, and they're not that expensive either. I just actually quoted some of these the other day, and they're not that expensive, from your quote, by the way. Solar heat gain 2. ACH is much tighter, but this is what's required for passive house. Well, it's a little bit different now, but around here, same temperatures. That obviously doesn't change. Remember what we had for heating, 21,000? Well, now we're less than 4,000. We've increased it, the R values, and we've reduced the air leakage, and we've brought our heating load down 500%. Now, this makes a lot more sense. And I would say that everything makes a lot more sense when you build like this, right?
Yep.
It just does. And if you're building new, come on. Is there a decision to make? Oh, but it costs so much more. No, it doesn't. It might cost 5, 10% more, but that's up front. Over the life of this, you're not paying 21,000 BTUs of electricity or heat and gas or whatever it is every year to keep this thing comfortable. You're paying 4,000 units. The payback's really quick. When California decided to go to net zero energy on all their new buildings, they figured that it would cost 10 to 15% more, but that the simple payback, and I read this in a HVAC article, but not only in the long term, they're saving people massive amounts of money in the entire state of California, not to mention better health, better comfort, better indoor air quality. How do you put a number on that, right? It's a no-brainer.
When you look at it from a monthly out-of-pocket, it's like 30, 50 bucks.
Say that again?
Monthly out-of-pocket in the short run, it's like 30 to 50 bucks. When you're looking at the long run, assuming a 3% to 5% increase in average energy cost per year, you're eventually ahead of the game. But initially, it's only like 30 to 50 bucks
Right.
different on new construction.
Right.
If you're amortizing it over a 30-year loan.
Right. And solar's even less. I mean, solar it increases your bill 10, 15 bucks a month for an average solar system. I mean, the payback's very quick. And over time, you're wasting money if you're buying from the grid. You really are. It's kind of a no-brainer. And if you don't believe me, give 3 or 4 solar companies a call and have them give you quotes, because you will see. It's pretty incredible. Okay, so we know that we want loads low. And most of these machines don't have the everyday machines that we're using. They might max out. Yes, we have the ability to do 500,000 BTUs. But the average system size for residential is about 50,000, maybe 60,000 and less. A well-built home, no problem. I can do 4,000, 5,000 square feet with 50,000. But I can't do my 1904 cinder block home with 4,000 or 50,000 BTU. I need 150,000 BTU. So simple stuff. Okay. Just so that I'm being responsible, if you're going to build really tight, we have to start thinking about air exchange and making houses sick by making them too tight. It's not that the house is sick. We breathe pollutants out. We cook. We are gassy sometimes. Whatever it is. If that never exchanges, that air becomes sick. The outdoor air is cleaner. We need to exchange that. And we need to control that in tight homes, because it's not going to naturally happen by leaks. Leaks are not the right way to make a home leak, or to make a home breathe and exchange polluted air. And we can talk more about that later if you have questions. But just note that this is part of what is required in tight homes now. So this is sorry, thanks, Todd. This is an energy recovery ventilator. So instead of just exhausting air outside, and for whatever gets exhausted, this isn't a balloon. It doesn't change volume. If a cubic feet leaks out, a cubic feet leaks in. If it's 100 degrees or if it's 0. We get that. That's just physics, right? So rather than bringing in air that's 0 in the winter or 100 in the summer, it goes across a heat exchanger, and we're able to recover the energy and the humidity from that. And these are very efficient units. We're getting close to 90+% efficiency on some of these now. And they don't use a lot of electricity, too, with some of the new ECM fans. So this is something that is required, I would argue, in every home. I have my 1904 home that's not incredibly energy efficient, and I don't have an energy recovery ventilator, but I do have a fan, an exhaust fan that's on all the time. Yeah, it costs me a little bit. But air quality is much better in my house because of it, and I measure it, and I know that. So we need some way to exchange air, okay? 2 questions. It depends. It depends on the install. I would say about $3,500 on average. I have 3 questions. Back first.
How do you measure indoor air quality?
So that's good. Great question. Great question. There are, I measure it with a FUBOT. So there are VOC monitors. There are new indoor air quality monitors that are coming on the market that are relatively inexpensive, but there's so much to indoor air quality. Is it CO2? Is it VOC? Is it soluble volatile organic compounds? Is it carbon dioxide or carbon monoxide? Is it particulates? There's so much. So I use a FUBOT, and it's pretty simple. It says, hey, my wife just sprayed her hair and the fan wasn't on, so it's red, and I can smell it. But it'll show me that, or it'll say green because my particulates are down. Maybe some other people have some other ideas, but there are other things that are coming on the market right now. So you had a question, sir.
In these heat exchanger units, you should have condensate developing as well.
That's correct.
What do you do with them?
It depends on the unit. So the question was, you have, in these units, you're absolutely right. So we have engineers here. I like that. You're creating condensation. You have cold air coming in, mixing with warm air. You're dropping the dew point, and you're going to have condensation. Some of these have drains, so they will drain to either condensate pump or drain to plumbing. Some of the energy recovery ventilators, like the Ultimate Air out of Canada, where they have really done a lot in building science with cold climates. Their enthalpy core is a hygroscopic material, and it can store and release humidity, and it never needs a condensate drain. Yeah, I don't know. Todd, actually, why don't you guys talk after this, because you know the ERVs, the ultimate airs pretty well. But it's a good question, and I don't know the answer to that.
It's out of Ohio, and I've had no problem with them.
With yours?
Yeah.
Okay.
And it's important to note there's HRV and ERV. HRV
Yep.
Drains the condensation, where an ERV transfers the moisture.
Yeah. Yeah, so an ERV has a core where humidity also can exchange. It's not just sensible heat, it's also latent heat, okay? And in some climates, we used to say HRVs for Colorado, ERVs for Texas. Now we're kind of thinking, hey, we like a little humidity even in Colorado in the winter. Let's do ERVs all the time. And I don't care, really. If your house is that tight, your humidity is going to be pretty tight. Now, we're not building in Texas here, and I don't know Texas. And I don't know Louisiana, but I know Colorado's pretty forgiving with this stuff. So ERV, HRV, I'm okay with either. You just need one. You need something to change air, okay? Couple last pictures. So other options. So I've said how great air source heat pumps are. Toasters are great too. Use a resistive heater. I'm okay with this. If your loads are 4,000 BTUs on a minus 15-degree day, okay, use a toaster. Save some money. Everyone wants geothermal. Geothermal's really expensive. Yes, it's efficient. But maybe the best thing in the world, I want a new Tesla. But maybe driving my old Corolla is the most efficient thing for a while, you know? So if you're going to replace it, get a Tesla. If you're going to build a new house, put in a heat pump. But you know, there's other ways to do it, okay? Evaporative coolers, I actually worked on that one the other day. The first pump I've ever had to change on these Breeze Airs. They're fantastic in this climate, very energy efficient, much more energy efficient than even these, but it's a different sort of cooling. It's wet, you know, it's humid. But it's not a sticky swamp cooler like we used to think of them. These are high-tech machines. And they're also expensive. These are about the same for cooling, but this is a whole house solution for large homes versus this might be for an efficient home, but not for Dr. Mark Erickson's home on the Fox Hollow Golf Course. You know, this needs that unit, and it works really well. Whole house fans work really well, but they're limited to the outside temperature at night, right? So we can open windows, but we can also want to force air through our homes. We want to take the heat away from the materials. We want that to run all night. The tile gets warm. The cinder block gets warm. The material, everything gets warm. So we want to force air through. Well, if it gets to 80 at night, I don't really want to keep it at 80. I want to cool it down. But on most nights, it does get quite cool. And in fact, EVAP coolers are cool because, pun intended, because they can operate like a whole house fan. You don't have to have the water on. But some people have allergies. Some people don't like the pollen. Some people don't want to keep their windows open. So they're not for everyone. But there are certainly other energy efficient options. This is in Munich. This gentleman, really interesting fellow. He owns some beautiful Porsches. This home, which is unbelievable, is heated by a wood fireplace. He has about a cup of ash that it creates every year. And he has, this is also from his house, he has earth tubes where connected to his ERV, so he's preconditioning the air through the earth, so he's making it even more efficient. But his home is heated, and it's 2,500 square foot by a log a week. It's amazing, absolutely amazing. Let's not go into this stuff. Just show you some quick pictures. There's a home in Boulder. This is the biggest one they make for this particular style. This is that right there. This is a near passive house. Does anybody know JP? What's JP's last name? He's an architect professor at CU, and this is his home that he designed. Pretty cool home. This is the one that I showed you. Now, you do have condensate, and this is a negative slope in this old 1940s house, so I had to use a hose basically to get the condensate out where it would drain this way and not back into the house and make the crawl space wet. So not the most beautiful thing in the world, but sometimes that's part of it. And so this is actually the condensate from inside. You notice that the lines are covered with this line hide material. This one, everything goes into the house and up, so you don't have anything on the exterior. But this, on the exterior, you can, basically it's like a gutter. You can hide everything in it. Some more pictures. This is Jim Smith's office in Golden. Note the solar. So we took Jim's large gas air handler furnace off the top of his building after doing some energy efficiency improvements, put a 3-unit mini split on. Now, he does have hail. You guys know that here. The solar's going to be fine in the hail, but these fins won't, so I covered it with diamond lath. You can buy that from Mitsubishi as well, but I just put it up there because this is so exposed on his roof that this is going to get pelted and then it's going to have to be replaced. This is probably the size of a pea. Anything that goes through there smaller than that, it's not going to hurt that much. So, cool application. You do need a qualified installer. They say that you can do this on your own. You can't. You need vacuum pumps. You have to know how to use dry nitrogen. You have to triple evacuate these systems to make sure there are 0 contaminants in these lines. You have to pressurize the systems to 600 psi. That's a lot of pressure. I've had a hose blow on me at that level before. I couldn't hear for a day. And that's doing it right, okay? We have to vacuum systems down to very low pressures. So again, make sure they're absolutely clean. It's not a do-it-yourself thing. You have to be trained in refrigerant, trained in evacuation, all of that type of AC heat pump type stuff, okay? Last slide, this is from Germany. Martin, this probably looks familiar to you. So this is right outside of Darmstadt, where Passive House got its rebirth 10, 15 years ago. Very common in the vernacular there to build with clay blocks with cells in them. But now they're not only building with those, they're wrapping it with 4 inches of foam to break the thermal bridges. And that's what that looks like in Europe in a lot of cases. Now, you can find ones that look like this too, but this is a heat pump. So this is the outside condensing unit for a heat pump for a very efficient home in Germany. So cool stuff. That's it. That's my contact information. I'm happy to take questions, and I appreciate your time. Thanks.